Welcome to this experiment on the kinetics of the iodination of acetone. When we're studying kinetic reactions, what we're interested in is determining the rate constant for a reaction. If we have a particular reaction here, our generic reaction A plus B going to products, the rate of this reaction will depend on the concentration of the reactants. And the level of dependence will be described by the order of reaction with respect to each of those reagents. So in our general rate law, we call K the rate constant, which is independent of the concentrations, so therefore it's constant and a useful measure of the speed of a reaction. And N plus M is called the overall order of reaction, and this describes the dependence of the rate on the concentration of the various species involved. We can study kinetic reactions in various ways. And in this reaction, we are reacting iodine, which is a very intense orange color, with acetone, and in the presence of acid, this forms iodoacetone and hydrogen iodide. So we get a colorless product. So here we are reacting our acetone and iodine, and we can see this color change in real time. So in this video, I've sped up the reaction process 10 times, but we can see as the reaction moves through time, the color of the solution decreases, the intensity of the color decreases as the iodine is used up and as we move to form products. So therefore we can study this reaction using absorption spectroscopy because the intensity of the iodine color disappears as the iodine is consumed in the reaction. Since we can measure this as a function of time, that means we can measure the rate of the reaction, the rate of change of our reactants as a function of time. So here's a kind of a schematic as to what's happening. We have our reaction mixture that we're measuring in our UV visible cuvette, and the concentration of our reactants decreases over time, so therefore we can measure the rate of reaction, which will be the slope of our decrease in absorption as a function of time at any particular time. So in our actual experiment, you're provided with suggestions for solutions A, B, C, and D. And if you look at these suggestions, what we'll see is we've been clever in designing the mixtures, because if we look at solutions A and solutions B, we'll see that the only difference is the difference in concentration of iodine. The concentration of iodine has been reduced by half. In other words, by comparing the rate of reaction A and the rate of reaction B, we were able to get a sense of the dependence of this rate of reaction on iodine. Similarly, in comparing A and C, we're changing the concentration of acetone, and in comparing A and D, we're changing the concentration of acid. So both of these experiments will give us information on how the rate of reaction depends on those concentrations. In other words, we're able to determine the order of reaction with respect to the concentration of iodine, acetone, and acid. You're then asked to make up a fifth solution, E, to further verify what you conclude. Now, the manual gives very, very specific instructions for using the UV-Vis spectrometer, but here we'll go through the general reaction protocol that you should follow. We have our reagents, A, B, C, and D, and so on. So here I've measured out my A reagents. The first thing we need to do is zero the instrument using the reference solution provided. So I'll fill up my cuvette. Note that the cuvette has a clear side, which is marked by an indented triangle. We do not handle the cuvette by these clear facing sides. These are the sides that will face the beam, and we don't want our thumbprints distorting that beam as it passes through the cuvette. So carefully handling my cell by the sides, I place the cuvette in the instrument. The UV visible beam in the instrument runs parallel to the bench, so I make sure my clear sides are facing that beam. We close the lid of the instrument and press the zero button on the instrument. Then I can remove that, and I'm ready now to set up for my experiment. So I get a clean cuvette and get my pipette ready to transfer my mixed solution. Once I mix the solution, the reaction starts, so we need to work efficiently. I pour one of the reagents into the other and then pour it back into the first glass so we get good mixing. Once I've done this, I can pipette in my solution into the cuvette, so somewhere between half and three quarters full is fine. And then again, carefully handling my cuvette by the sides of the cuvette, I place the cuvette back into the instrument and now press the acquisition button to start collecting my data. We'll note as time goes on that our absorbance is decreasing. This is because the color of the iodine is decreasing. You should see in the reaction flask that you have with the mixture that color will decrease over time as well. Finally, then we get our initial our decrease. The manual describes how we get the slope of this graph. Note this is absorbance per minute. You should do this because sometimes putting in the USB key jams the instrument. So a clean USB key is provided, so insert it into the instrument, save your file using your initials or something sensible, and then once you've saved it, you can use the text file that's generated in Microsoft Excel or in Origin to draw your graph and obtain the slope. You're going to repeat this experiment then for solutions C, D, B, C, and D, and of course the solution that you make up, solution E. When you're done, make sure all waste goes into the waste solution divided because of course there are some organic reagents in our solutions. So this rate that we quantified either from our instrument or better still from the data we extract on the USB key, if we determine the rate of reaction from the initial rate, in other words, the initial linear part of this graph, this will give us the rate of reaction for each of our solutions A, B, C, D, and E. And again, as we said, we know the fact that we have buried one reagent and held all others constant between our series of experiments means that we can determine the order of reaction with respect to each of those reagents. That means then we can build our rate law. We can say what the rate law is because we'll know the dependence of each of the concentrations. So the manual gives you a prompt on how to do this. So in your data analysis, then you will have rates from the data from the instrument. So here they're in absorbance per second. You need to make sure your time units are consistent. And then given the extinction coefficient of iodine, we can convert this into the more usual form of rate, which is dm cubed per mole per second. How is concentration changing over time? And then knowing the rate law, knowing the rate and the concentration in each case, we can work out our rate constant, which is the purpose of the experiment. The rate constant is a constant value, so you should be able to calculate the mean standard deviation of this value. In discussing your results, then you want to think about, well, why is the rate law what you've concluded? So you should refer back to the mechanism of this reaction, and you'll see that the rate determining step, in other words, the slow step in the reaction that determines the overall rate of reaction, have a look and see what that involves. Why does the rate law matter? Why does the rate law depend only on some of the reagents in the reaction and not on others? That should be a major part of your discussion.